Welcome back to this topic on deploying models. So far, we've been talking about actually deploying the model in the AI inference engine, where we actually save the trained model in different formats, whether it's in the TensorFlow safe model format or in the HDF5 format or in the ONNX file format. Now, once the model has been actually saved, and you actually want to run the software in the AI inference engine, be it NVIDIA TensorFlow RT or the ONNX runtime, we still have one remaining problem, and that is actually how does the application actually send the query to the runtime engine, right? How does it actually receive the query? And this is what we're going to be talking about in this series of slides. So the way that the AI inference engine actually receives a request from the end user or from the end user application is actually through this mechanism called REST Web Services. So back to this diagram that we had shown earlier. So we talked about the training and inference engine so far, and notice that at the end user application actually sends a query to the prediction service or the AI inference engine. And the AI inference engine will make use of the model information and then make a prediction and then send back the result to the end user. So this interface here is what we're going to be talking about in this series, like the REST web service interface. Now there are different ways of actually creating such a service, but I will be describing at least two of them. So let's talk about REST web services. What does it actually entail, and what does it actually look like? So this is actually a system diagram showing you the end user application, the client, which could be a browser. So the browser will actually interface with a web server. So you would deploy a web server, for example, the NGINX, a very high-speed web server. And this web server will receive the request or query from the browser and then send it to your code, your model code, right? Your model code that you have saved earlier, it needs to be retrieved and then running in the AI inference engine, then basically generate the prediction using the data that's coming in from the query. So there is actually your web server actually may not be able to call this model code directly, so it needs to go through some sort of translation or gateway code, and which is what this Gunicon WSGI server is doing. It's actually a translation code to actually call an internal Flask Python based server, which then calls the code that you have saved as your save model. Then once this save model actually generates the result, it goes back in the reverse direction through the Flask API back to the Gunicon gateway, and then back to your web server, and finally the information is sent back via HTTP protocol to your web browser. So we'll talk about the whole process of actually sending a request. What's the shape, what's the URL that you actually would present here at the web server, and then how it's actually translated to the Flask and Gunicon, and finally to your how is the information then picked up from the safe model. So we're going to talk through the whole process here. Now the entire infrastructure could be actually contained within one single Docker container or virtual machine, or we could have separate Docker for the web server, a separate Docker for the backend, which is the Gunicon plus the AI inference engine. So you could actually put everything in one single Docker container. We may for better load balancing, separate it out into different containers to run these different parts of the code. Or you can have a three-tier structure. The web server in one container, another container containing a Flask and Gunicon, and lastly the backend, which contains just the model inference engine. So three containers. So various configurations are possible. So this set of slides just describes in further detail the previous diagram. So the NGINX web server, this is actually the front end, which it's a direct interface to your browser. So any request coming in from your application in the browser comes to the NGINX web server, and this actually then connects to the Gunicon, meaning users will hit the NGINX from the browser first, and then it forwards this request to the Gunicon. Now the Nginx will face the outside world as it serves other sort of files besides just the data being generated by your Python code. For example, there may be static information like images, CSS, HTML, and so we don't need to go talk to the GUNICon to retrieve all this. All this can come from the Nginx directly and from the file system attached to it. However, it can't talk. The Nginx doesn't understand Python directly. So to talk to Python-based application, it needs a Python-based application, the server like Flask. So Nginx, being a web server, needs a gateway, the WSGI, which is a gateway in order to act as a bridge to talk to the Flask. So the Flask is the one, is a Python-based application server that talks to your model serving code directly, since both of them are Python-based. So Nginx sits in front of the GUNICon, which is the bridge, and then this GUNICon actually forwards the request to your Flask application. And note that the Flask can also implement WSGI interface within it. So actually, you may not need to have a GUNICon, but GUNICon is the more efficient implementation of this WSGI. So for production use, you're advised to use something like GUNICon instead of trying to use the Flask to implement WSGI directly. But we have added GUNICon because GUNICon works internally by handling most of it before calling your Flask code. This is done in a parallel manner by having many workers ready to handle the request instead of one by one in a sequential one by one manner. And so it actually is able to serve this request a lot faster than what the default Flask server does. The end result is that your application can handle a lot more requests per second. And we can use one single container to have everything, or as I mentioned, we can have two containers where one container is just containing the Nginx, the web server, and another one to have the GUNICon, Flask, plus the backend code, right, the AI inference engine. Or we could have a three-tier where one is the Nginx, another one for the bridge, and then yet another one for the last tier, which is the Python code itself. So that would be a bit complicated. So normally, I think two would be sufficient to do the job for us. So what is the WSGI, or Web Server Gateway Interface? Basically, this is a bridge. Okay, the Web Server Gateway Interface, or WSGI, is simply a calling convention for web servers to forward requests to web application frameworks written in Python programming language. So the current version of the WSGI is actually 1.01, and it's actually specified in the Python Enhancement Proposal PEP 33333. The WSGI has two sides. One is the server side, which is facing the web server. So this is often running a full web server software such as Nginx, what's facing this Apache or Nginx, or it could be a more lightweight application like this one. Okay, FLUP. The application side is the one that actually talks to your Python framework. In which case, this will be your serving your AI inference engine, right? So one side faces the web end, the other side faces the more Python-based part of your code. In our case, we also put in one more layer, which is the Flask layer, to make the calls accepted from your GUNICon, and then from the GUNICon, it goes through this part to actually call the AI inference engine. Now, WSGI is implemented by Flask, but it's also implemented by some of the popular engines such as GUNICon, and also something called the CherryPy, which is a pure Python-based implementation of this. GUNICon, I believe, has some code that is not Python-based, but it's very efficient parallel with many worker threads. So it's a very popular WSGI gateway for this type of applications. There is a variation of the WSGI called the asynchronous WSGI, or asynchronous server gateway interface, so ASGI. It's actually a successor for WSGI, and it's intended for asynchronous web servers which are able to run in a more multi-threaded manner. So they're able to handle more requests per second than the traditional WSGI interface, and also more lightweight. So where WSGI provides a standard for synchronous Python applications. ASGI provides it for asynchronous as well as synchronous applications. So it's actually backward compatible with WSGI. And there are several implementations of this. ASGI really would be a big advantage when we have more parallelism if we have a multi-core CPU. So you have a 4-core, 6-core, 8-core CPU, and you can run many threads in parallel. The ASGI interface will be more efficient. And you can see that for the ASGI, there are actually a number of implementation, Fast API being one of them. And then we have something called the UVCon. It's actually very similar to GUNICon, but this is for the asynchronous WSGI interface rather than the synchronous one. This is still very much in development. Of course, there are some implementations like this too, but as compared with WSGI, this is not as mature, but it has the promise of giving you more performance. So far, we've been talking about the infrastructure or the servers that you need and what is implemented on each of the servers in order for your browser to send a request or query to your model and then retrieve the result from the model and send it back to the browser. Now, what is the style or format of the messages that's actually interchanged between your browser and the web server, and then from the web server to the WSGI interface? So what we're going to be describing is this format or style of doing the interface, and it's something called REST-based web services. So REST actually is a short form for representational state transfer. So what we are trying to do is this is actually a software architectural style that was created to guide the design and development of query systems that are based on the World Wide Web architecture, which is basically your browser architecture. Now, RESTful Web APIs is purely based on what actually runs from your browser to your server, from your typical web server. So we're actually not inventing a new computer communication protocol. We are merely reusing the popular and well-established browser web protocols called HTTP, Hypertext Transfer Protocol, in order to do this query mechanism. So we are sort of borrowing the protocol that's been established for the World Wide Web in order to make these queries. So this is great because there's already many implementations on various computer hardware of the World Wide Web protocol. So you don't need to reinvent the wheel. We're just going to borrow it in order to make our queries. So the APIs or the application programming interfaces is entirely based on this HTTP methods. And what's key to access a particular resource or a particular function call, in this case, would be to make use of the URL or the web browser address, right, that you typically find at the top of your browser. So this URL will encode information like what is the resource, what is the query about, right? Are you trying to get the prediction about a particular variable, or you're trying to get a prediction about a certain service within the server? And other information could be passed via JSON data or XML data. So this is all supported by the hypertext protocol. So we're just borrowing the same format and making some adjustment in terms of the URL we use and a certain way of using the standard HTTP methods. So what REST provides is a way to make the API calls via the HTTP request methods of put, post, get, and delete. These are actually standard methods that are implemented in every web browser and also every single web server. And we provide a suitable URL so that we can actually access the suitable resource or function within the server that we want to actually use. So the URL could be pointing to a particular model, or could be pointing to a particular variable or output in the model that we want to get. So it's very flexible because you could actually separate with / to separate different resources. So how does this actually go? So HTTP, which is actually the web browser protocol, actually works in a call and response or request and response manner. So you can see that the web client below, it sends the HTTP request to the web server. The web server receives the request and then interprets the content of that request in which case the verb here is get. So it's actually going to get a particular resource, which is a HTML file, a web file from the server located at /index.html. And the rest of it is just additional information about the protocol type as well as the DNS name, the host name. So the server, when it receives it, knows that actually the request is about getting this resource. So it'll go into the file system, find the index.html file, and then return this file back to the web client with the content after this, and there's some header in front to just tell it that everything was okay, 200 okay, you can display the content. Otherwise, if there was no index.html file, then instead of saying 200 okay, we'll say 404 error, resource not found, so that the web client will display the error message rather than just the content that's being retrieved. So because in this case, the content was not available. So HTTP is the foundation of all communication in the World Wide Web, where hypertext documents, including hyperlinks to other resources, are easily accessible. So for example, a mouse click or by tapping on the screen on the web. So incidentally, when you click on the link, it will send a new GET request, and the resource is actually the address that's inside the link. So HTTP allows parameters to be specified in the URL, and it can also be passed as additional messages or content information within the request itself. So after this three ellipses, the dots here, right, there may be additional information like HTML or text or even JSON or XML data. So you can actually have additional data being passed in the message itself. So it goes by request and response, and every time the request goes across, it's actually placed within what we call a HTTP message. And the response also comes back in another HTTP response message. So it is very much like sending letters and getting a response back from the server. So each of these letters or messages is actually tied to either request or response. So the REST-based API, which we've been talking about, basically is layered on top of this communication mechanism. So you will still make use of a HTTP request, and you make use of the GET methods, makes use of the return error codes. But what it actually tries to add on to this is actually to customize the URL so that you know what resource we're getting. And we're going to use the GET, put, delete, and post messages in a particular manner, right? So it's not exactly the same as your typical web interaction, because the GET has a special meaning for REST-based APIs, and put and delete and post as well. So we come into this shortly, but just understand that actually the requests are the same as the normal web server. So the HTTP messages, which I mentioned just now, when the browser sends it across, there's a particular method or action, and then there's a URL, and then there are some additional. So the first part is what we call the header information, and then after that we have the content, which is the body of the message. Is that okay? It may be a very large file. For example, you're actually trying to do a file upload. The header will contain just what is the file name, etc., but the body may contain the actual content of the file. So it can be very large. Okay, so HTTP messages are how data is exchanged between the client and the server, the browser and the web server. And there are two types of messages: request, which is sent from the browser to the server, and response, which is the answer being sent back in response to the request. The HTTP messages are basically composed of textual information, right? So they are normally multi-line. So for HTTP 1 and earlier versions of the protocol, these messages were openly sent in the connection, but in later versions, they are actually encrypted or even compressed, so that now there's a performance improvement in the way. But the essence is the same, it's just some optimization on the exact formatting of the messages. And so the first part is the header information, and then after that we have the body, which contains the data, and it's in both directions, either forward to the server. This is the HTTP 2, but you can see even in the HTTP 1 version, the original version, there's multi-lines containing header followed by the body, which contains the data of the request. And with that, we come to this end of this first part. We'll continue this discussion on REST-based services, how we can effectively make use of a very well established communication protocol for the World Wide Web to actually now make it use for it for sending programming function calls from a client application to a server application. Thank you for your attention, and we'll see you in the next set of videos.